All right. So for the last talk of today's session, we have Ariel Kellison. She's now at Galois, previously at Cornell, and she's going to be talking to us about a very interesting piece of work looking at scalability for floating point backward error analysis by leveraging a bunch of ideas from type theory. So Ariel, please.
Thank you. All right. So this talk is about Bean, a language for backward error analysis, designed and implemented by me, as well as Laura Zielinski, David Bindel, and Justin Shu. So why did we develop Bean? And I had to take a moment to think about this slide in particular because of the keynote talk this morning. What can PL do for people? I actually think that in terms of numerics, PL really has an opportunity to make a big difference in the lives of people, specifically because numerical results are often used now to inform policy decisions that affect all of us. So in particular, we have some examples here. Energy demand forecasting shapes infrastructure planning. Disease spread models inform public health responses, and we actually saw the use of this during the COVID-19 pandemic. And drought projections are essential for effective resource management and also for climate policy. So today I'm going to talk a little about how we can use PL to help us ensure that we have trustworthy numerical results in settings like this. So these forecast models and projections, they're all computationally demanding. They rely on billions, if not more, of floating point operations. But as we know, floating point math is inherently approximate. So every floating point operation, an add, a multiply, a divide, a subtract, introduces some small rounding error, potentially. And while each individual rounding error is quite small, these errors compound over billions of floating point operations, and they can grow too large. And our results, these forecast models and projections, the results of these models, can become untrustworthy. Thus, we need to be able to analyze these errors statically before we ever run these costly computations. So if you look in a numerical analysis textbook, you'll generally see two approaches to error analysis. The first approach is called forward error analysis, and it answers the simple question of how close is the computed result to the exact mathematically correct result. So in simple language, is your floating point result what you would expect? And the second approach is a little harder to state in plain language. It's slightly more complicated. The second approach is called backward error analysis, and it answers the question, how much would we need to perturb the input to an exact function so that it produces the computed result? And I'll explain this in more detail during this talk. So for our first approach, there are several existing static analysis tools that automate forward error analysis. These include DAISY, Precisa, FP Tuner, FP Taylor, and Numerical Fuzz, which we introduced at PLDI last year, as well as many others. And some of the authors for these tools, I think, are in the audience. Unfortunately, for the second approach, and this is a common approach that you would see, again, in a numerical analysis textbook. It's very important in the field of numerical analysis. For the second approach of backward error analysis, which is the topic of today's talk, there are no existing static analysis tools that automate it. So if you're a numerical analyst and you want some backward error analysis guarantee, there isn't a single tool available for you to use. And of course, this is where our contribution comes in. So Bean is the first static analysis tool for backward error analysis. It's a first-order language with numerical primitives and a linear coeffect type system designed for tracking backward error. Now, Bean has three important properties that we think are generally good for languages for error analysis. First, Bean is sound. That means that well-typed programs in Bean satisfy the backward error bound that the type system assigns them. We'll see some examples of soundness, sound programs in Bean momentarily. Secondly, Bean is useful. It infers automatically error bounds that match worst-case theoretical error bounds from the literature. So there are well-known backward error bounds from the literature for problems that we'll go into a little more detail on today, and Bean can infer these bounds. And finally, Bean is fast. So error-bound inference right now scales quadratically with the number of floating point operations in a program. And while this might not seem too fast, in the terms of rounding error analysis, this is quite good. All right, so to understand how Bean works, we first need to understand the concept of backward error analysis. We can consider backward error analysis for an exact map f, and its floating point approximation tilde of f. So if we know that our floating point approximation maps a point in the input space to a point y in the output space, a backward error analysis identifies another, possibly different point from x in the input space, denoted here by tilde x, that maps under our exact function back to the computed result, so back to our floating point result. And a backward error analysis not only identifies this additional point in the input space, tilde x, but it also bounds the distance between x and this new point tilde x. And we will refer to this bound here as alpha. So alpha is showing the distance between these 2 points in the input space, and that is our backward error bound. Now, a small alpha is desirable. A small backward error bound is desirable. This means that the floating point program won't magnify rounding errors. So again, on the first slide, I was saying that over billions of floating point operations, it's possible that models and simulations would magnify errors so that they become too large and we can no longer trust our results. But if we have programs with small backward error, then we know that that program is well behaved in the sense that it won't magnify our rounding errors too much. All right, so we can better understand backward error analysis with a simple example of a dot product. So in this case, the exact dot product is what we're all familiar with. It's the sum of the product of the individual components of the two vectors. And we can implement this in floating point arithmetic in a language like Python using a simple for loop. Now the goal of a backward error analysis is to find an alpha, our backward error bound, such that our computed floating point result equals the exact dot product over two perturbed vectors. These perturbed vectors are denoted by tilde u and tilde v. And these two perturbed vectors are within a distance of alpha of our initial inputs. So that alpha, again, is our backward error bound. It's bounding the distance between our perturbed vectors and our original inputs. Now, how we would traditionally do this by hand or in a numerical analysis textbook is we would apply a backward error model that characterizes the backward error of each of the individual floating point operations. So for example, a floating point addition is exactly equal to exact addition over some perturbed inputs that are within a distance of machine epsilon from our original inputs. Similarly, the backward error model for multiplication says that floating point multiplication equals exact multiplication over some perturbed inputs that are within half of a machine epsilon of our original inputs. So this is nice, right? It tells us what is the backward error for each individual floating point arithmetic operation, but we have many such operations in our dot product. We still don't necessarily know what alpha is. If you were to, again, look at a numerical analysis textbook, there would be several pages for describing how to compose these backward error bounds for each multiplication and each division to actually get an error bound alpha for our dot product. That's where Bean comes in handy. So we have an implementation of Bean that's based on numerical fuzz, which we introduced last year at PLDI, as well as dfuzz due to Azevedo de Amorin and co-authors from 2014. All right, so this example is an implementation of dot product of two vectors u and v and r squared. So a simple example of vectors with two components in Bean. So this is our Bean program. Okay, so yes, it takes a dot product of these two vectors. Now first we deconstruct u and v, so we get the individual components of our vectors. We sequence the computations of the multiplication of these two components into the final addition. So again, this is just two vectors with two components, a simple example. And now, while this example for a Bean program shows multiplication and addition, we also, of course, have subtraction and division in our language. So we have all of the basic arithmetic operations. Now, if we run our type inference and type checker on this Bean program, it will tell us the return type of the program. So our dot product, we would expect to return a numeric type, and that's exactly what our type inference and type checker says. It says that if we evaluate this program, it will return a value of our new primitive numeric type. But our type inference also, for Bean, also tells us an additional piece of information, which is very important. It tells us the context that this program is well typed in. So, in particular, from this type inference to the exact guarantee that we have in Bean, our backward error guarantee in Bean for this specific program says that for any vectors u and v in R squared, there exists these perturbed vectors, tilde u and tilde v, such that our Bean dot product over these initial inputs, it equals an exact dot product over these perturbed inputs, and the distance is bounded. Sorry, this isn't showing. So, whoops. And the distance between our perturbed vectors and our initial vectors is exactly what we call here this coeffect annotation that was inferred in Bean. So Bean infers these backward error bounds, and the soundness of our type system actually guarantees that all well-typed Bean programs satisfy some kind of backward error guarantee. Now, for those of you that are familiar with backward error analysis, you might be a little bit surprised here. Why should all programs satisfy a backward error guarantee? This is actually a really challenging problem because many programs that you are familiar with, such as matrix-matrix multiplication, they don't actually satisfy a backward error guarantee. So how did we design a language in which all of the programs have a backward error guarantee? And the issue at hand here is that really not all rounding errors that are introduced during the execution of a program can be interpreted as small perturbations to the input of an exact computation, and that's what we need in order to establish a backward error bound. Okay, so this is in stark contrast to forward error analysis, that first approach that I said was usually treated in the static analysis literature. Okay, so for forward error analysis, all programs have a forward error bound. So this is a really big difference, just to repeat, between forward error analysis and backward error analysis. Not all programs have a backward error bound, whereas all programs have a forward error bound. For instance, they can have a trivial forward error bound of infinity. All right, so how did we deal with this main challenge? Well, our contribution is what we call backward error lenses. Now, programs with backward error guarantees, we think, are characterized by backward error lenses. So there's really kind of been a gap, as far as we're aware, in the numerical analysis literature for characterizing kind of the set of programs that have backward error guarantees. Often there will be a backward error analysis for specific algorithms or specific programs, but really in programming languages, we're interested in defining kind of the set of programs that have a certain type of guarantee. And we believe that these types of programs are characterized by what we define as backward error lenses. All right, so a backward error lens from input space X to an output space Y is characterized by three transformations: a forward transformation and an approximate transformation. So we've seen these so far. The forward transformation we can think of as our exact program, computed in infinite precision. And our approximate transformation here, we can think of as our approximate or floating point transformation. But this backward map is new. This backward map is an explicit transformation that takes a point in our input space, a point X here in our input space, and a point Y in our output space. It maps both of these to another new point in our input space. That's our characteristic backward error point X tilde. Now, it's important that these maps satisfy two conditions that we call reconstruction and our backward error bound. And really these two conditions are saying that our approximation map, this forward map here, which would represent like our floating point program, this approximation map has a backward error guarantee. So that's what those two conditions that our transformation, our backward error lens must satisfy, that's what those say. Now, we called these backward error lenses, kind of looking at the programming languages literature from the lenses for the view update problem from Foster and co-authors from 2007. So going all the way back to 2007, this is kind of, we renamed or rewrapped the idea of lenses into this concept of backward error lenses. All right, so we give being a semantics in the category of backward error lenses. And so in this category, objects are distant spaces, morphisms are backward error lenses, and then we derive our soundness guarantee that we briefly introduced earlier from the properties of these morphisms. So how well does this work in practice? So evaluation results show that being works well on programs with known backward error guarantees. So in our evaluation, we show that being infers optimal sound error bounds. So I'm hoping you all can see this table in the back, and I know it's a little bit late, so I'm going to have these little pointers to help guide us through this table. All right, so again, in our evaluation, being infers optimal sound error bounds on these benchmarks. 3 of these benchmarks are from linear algebra. We look at a sum, dot product, matrix vector multiplication. And 2 of these benchmarks are from polynomial evaluation. So this is a Horner's scheme and then just a traditional polynomial evaluation. All right, and these benchmarks are increasingly large input sizes. So for example, this is a sum of 50 values, 100 values, 500, 1,000, and so on and so forth. And so you can also see the increasing number of floating point operations in each of the benchmarks. And we ask the question, does the bound inferred by being, the backward error bound, does it match the theoretical worst case error bound from the literature? That's what we would like to know. And indeed, this blue check mark says yes, indeed, being does infer optimal sound error bounds for each of these benchmarks. Okay, and that is our evidence for being useful. Now, is being fast? Well, there's really not much to compare it to since it's the first static analysis tool of its kind. But as I said before, right now it scales quadratically with the number of floating point operations, we believe, in each of these benchmarks. And so we're going to claim that it's fast until someone can do better. I'm glad you thought that was funny. Okay, so in summary, Bean is a language for backward error analysis. You see the acronym where it came from. It's a first order language with numerical primitives and a linear coeffect type system designed for tracking backward error. It's sound, it's useful, and it's fast. And it's the first static analysis tool for backward error analysis. So you can see our paper or our GitHub repo for more information if you'd like. For example, we have a lot about language features, cool language features in the paper. So if you're like really a PL person and you think the idea of dual context, linear, nonlinear coeffect type systems is really your jam, take a look. We also have examples for the real numerics people in the audience. We have a backward error analysis of triangular linear solver using Bean, very cool. We also have implementation details, so a soundness and completeness results for the type checking algorithm, as well as additional details about our semantics. So if you're a PL semantics person, the definition of the category of backward error lenses is really neat. So take a look if you have a chance. And then just one final thing. I will be going out with one of the interns from Galois. I'm a research engineer at Galois. We are going to go and have drinks around 5 p.m. So if you see me or the intern from Galois, we will buy you a drink here in Seoul. So thanks so much for coming to my talk.
All right, we got a lot of questions.
Oh no.
Hi, thanks for the great talk and the really cool work. This is Rachit from MIT and Jane Street. Can you give some intuition of what causes a computation to not have a backward analysis map?
Yeah, so it's kind of, it's an interesting question that like doesn't have the best answer. So much in the sense that like really, if you look at the numerical analysis literature, you're going through this process, again, of just assigning backward error results to each of the individual floating point operations and trying to compose those together and seeing whether or not those rounding errors can be interpreted as perturbations to the input of an exact computation. So for example, I said matrix multiplication doesn't have a backward map, but in particular, or a backward error result, but I think what you're asking potentially is which computations cannot be embedded or interpreted inside of this backward error lens semantics. And that's a really good question that I don't know that I have an excellent answer for, to be honest, because, well, really these types of programs sort of fail to have they fail to satisfy one of these two conditions. And which one of those conditions they fail to satisfy is not necessarily clear to us a priori right now.
Thank you.
Yep.
Hi, thank you for a wonderful talk. I have a very specific question which arises a lot in machine learning. Floating point arithmetic is not commutative, which means if I try to do an addition operation with a bunch of floating point numbers, they may run in parallel and you may get different results.
It's not
Sorry,
associative,
did I say
but
commutative?
it is commutative.
Sorry, I apologize. It's not
actually,
associative.
Okay,
right?
yes.
And this shows up all the time, and some of this is a function of the runtime behavior of how you're executing these operations in parallel versus sequential. So do you have any thoughts or comments about the interpretation of this language or this analysis that you're doing?
Yeah, so you're saying the static analysis actually isn't accounting for some of the runtime behavior.
That's correct, yes.
Yeah, so really what we're trying to do here is design languages and static analysis tools that emulate the type of analysis that a numerical analyst would do. So it's a very high-level analysis that really isn't going down to that kind of level of granularity that you're talking about. Yeah, so that would kind of be a different research problem.
My name is Hiramishi from JJ Inc. And I once heard that, so I'm so impressed that you used lens to
That's right.
formalize the backward adder and the think of the category of the lenses. And one thing I can remember is that there is some study on automatic differentiation realized with lens and the category of such lens. Is there any relation to this?
You know, I'm not that familiar with the semantics or like using lenses in the field of autodiff, but that sounds very interesting. I'm sorry, I don't know that I have necessarily anything to say about that, but it's a very interesting point. Yeah, I think lenses really appear in all of these different places. In kind of like computational mathematics, they've appeared in machine learning and so on as well for semantics. And I do really think that we're not just trying to like shoehorn everything into lenses. I think that they are just kind of a very general construct that provides insight that maybe other mathematical constructs for semantics for programming languages don't necessarily do. Yeah.
Okay, last question.
Hi, I'm Bhargav from the University of Utah. So this was a question about the error model used in the paper. It's not the 1 plus delta error model, but like it's something different, the epsilon e to the power delta like error model. And then like we've talked a lot about backward and forward error, and they're related by a condition number. So the work we have done kind of shows that although you won't get tight bounds with just by taking condition numbers into account, you can at least try to localize the error to the specific operations that do like amplify error by a lot.
Yes.
But the problem is when like these condition numbers are closed form, but they can themselves be pretty inaccurate, and you won't get like the right amount of amplification.
Okay.
So maybe like, do you know if the e to the power delta error model has a closed form analog of condition numbers that we could use to like calculate more precise amplification factors?
That's a really interesting question. So there are only a few papers that kind of use this e to the delta rounding error model instead of the 1 plus delta rounding error model, and I think they're mostly from like the 70s. So it really hasn't been developed out, I think, in the way that it could be that you're describing. I think that's kind of an open area of work that I'm really hoping to see progress. Yeah.
Okay, thank you again for Ariel. Round of applause. All right, so that closes out the session on numerics. The program committee was so kind as to give us numerics people extra time for coffee and snacks, which I think shows how much this is a valuable line of work for the community.